Amazing day for today. We're going to have the polynomial function. Here are some basic features of graphs of polynomial functions. So a graph of a polynomial function is continuous. This means that the graph of a polynomial function has no breaks, holes, or gaps. So if ever you have seen, the first graph is a polynomial function, and the other one there is a break. No. So this graph is not a polynomial function. Another feature of a graph of polynomial function, a graph of polynomial function has only smooth, rounded turns. No? A polynomial function cannot have a sharp turn. So this one is a graph of polynomial function, and the other one is not a polynomial function, since this is not smooth, rounded terms. No? So these are examples of graphs of polynomial functions. These are graphs, no, of not a polynomial functions, since there are breaks, no, holes, as well as it is not having smooth turns. So these are example of not graphs of a polynomial function. So let's have the end behavior of polynomial functions. So the behavior of a graph of the function to the far left and far right, these are said to be the end behavior. So although the graph of a polynomial function may have intervals where it increases or decreases, the graph will eventually rise or fall without bound as it moves far to the left or far to the right. So how can we determine the end behavior of polynomial functions? So we can only look on the term with the highest degree. So let's have the leading coefficient test. So look for the term with the highest degree. So is the coefficient greater than or less than 0? Is the exponent even or odd? So the answers to these questions will help us to determine the end behavior of the polynomial functions. So let us see. So if the leading coefficient is positive, even an even degree to its variable, so the graph rises to the left and rises to the right. Now, so if the leading coefficient is negative and we have even degree to its variable, the graph falls to the left and falls to the right. So in here we have a -1 as your leading coefficient and 2 as your degree. So how about if you have a positive leading coefficient, just like in here, a +1 and an odd degree to its variable. So we have 3 as odd. So the graph falls to the left and rises to the right. Okay, so if the leading coefficient is negative with an odd degree to its variable, the graph rises to the left, okay, and falls to the right. Okay, so these were the wherein you have their factor that can no longer be factored using coefficients that are real number. So the graph of any type of function must pass the vertical line test. So the graph must have first the graph must pass in the vertical test in only one point. No? Every polynomial function with real coefficients has the set of real numbers at its domain. This means that the graph of a polynomial function has no breaks, holes, or gaps. What else? The polynomial equation of the n degree cannot have more than n roots. So this only means that the graph cannot intersect the x-axis more than n times. Number 4 characteristics of a polynomial function graph. So the graph of a polynomial function has only smooth, rounded terms, as what I have said earlier. So a polynomial function cannot have a sharp turn. So these are features of graph a polynomial function. So here's a polynomial function. So it can be shown that for a polynomial function of degree and the following statements are true. The function has at most n real roots or zeros. So the graph has at most n minus 1 turning points. So how are you going to have the turning points? That is n minus 1. So degree minus 1. Now, turning points, relative maximum or relative minimum, are points at which the graph changes from increasing or to decreasing or vice versa. So, the series of polynomial function are the values of x, which make f of x equals 0. And these values are the roots or solutions of the polynomial equation where x is equal to 0. So, all real roots are said to be the x-intercept of the graph. So how many turning points do we have in f of x equals to x cubed plus 3x squared minus x minus 3 half? So let us set the equation x cubed plus 3x squared minus x minus 3 equals 0. So let us use negative 1 as our divisor. So we have x equals negative 1. So bring down 1. 1 times negative 1 is negative 1. 3 minus 1 is 2. 2 times negative 1 is negative 2. Negative 1 plus negative 2 is negative 3. Negative 3 times negative 1 is equal to positive 3. Then negative 3 minus plus 3 is equal to 0. Therefore, negative 1 is a factor. And then let us use positive 1. So 1, bring down 1. Then 1 times 1 is 1. 2 plus 1 is equal to 3. 3 times 1 is a positive, is a negative 3. Negative 3, this must be a positive 3. No, negative 3 plus 3 is equal to 0. Then 0 times 1 is equal to 0. And then, no. So, therefore, positive 1 is also a 0 of the function. So, what are the zeros of this? So, we have negative 3, negative 1, 1. So, these are said to be the x-intercepts. And the y-intercept is a negative 3. So in this one, let us identify the degree, the function. So the degree of the function and the highest exponent is positive 3. And we have the turning point. So how are we going to get the turning points? So the turning points, we must have n minus 1 or degree minus 1. Since the degree is equal to 3, so we're just going to deduct 1. 3 minus 1 is equal to 2. Therefore, the turning points that we have is 2. So let us see. So since we have a positive leading coefficient and then we have an odd degree, so it falls to the left and it rises to the right. And then it will be, the y-intercept is in the negative 3. And then we have negative 3. We have negative 1, 1 as the x-intercepts. So the graph will pass through to negative 3, negative 1, and 1 in the x-axis. And then in the y-axis, the graph will pass through negative 3 since negative 3 is the y-intercept. Again, how are we going to get the y-intercept? The y-intercept, we're going to just let x equal to 0. And then the value will be the y-intercept at the point wherein it will pass through the y-axis. So how many turning points? So we have 2 turning points. So we have 1 turning point in here and the other one is in here. So this is already the graph. How about the multiplicity of 0? So the multiplicity of a 0 is the number of times the real root of a polynomial function results in f of x equals to 0. Suppose R is a 0 of even multiplicity, then the graph touches the x-axis at R and bounces at R or is tangent to point R. Suppose R is a 0 of odd multiplicity, then the graph crosses the x-axis at R. Regardless of whether a multiplicity is even or odd, the graph tends to flatten out near zeros with a multiplicity greater than 1. So let us solve for the zeros of f of x equals to x squared times x minus 2 squared, then show the graph. No? So we have x squared equals to 0, so we have 0. X squared equal to 0, so we have 0. So we have multiplicity of 2. And then for a positive 2, we have multiplicity of 2 as well. So the exponent tells us the multiplicity. Therefore, in here, so it is said to be, it must be tangent to the x-axis at point 0, 0 and 2, 0. So we have a positive leading coefficient, and then we have an even degree. So it will be rise to the left and rises to the right as well. And then, so the multiplicity, so we have in here 0 and 0, 2 and 0. Okay? So it is tangent since it is a multiplicity of 2. Okay, let's have the behavior of polynomial function. So the behavior of the graph of function to the far left and the far right is the end behavior. So as I said a while ago. So using the table on the next page, no, on the next slide. So we're going to observe how the end behavior of the graph changes in relation to the leading coefficient and the degree of the polynomial function. So these are the given polynomial function. So in here, if the this one is all about the leading coefficient. If we have a positive leading coefficient, so we have a sub n greater than 0. Then if we have a negative leading coefficient, so we have a sub n less than 0. And then in terms of the degree, so we can notify the even or odd degree. And then this one is the example graph of the polynomial function. And then in here we have the behavior in terms of the left hand and the right hand. So it can be rising or falling. So let's have the first one. If the given is a positive leading coefficient with an even degree, wherein we have f of x equals to x squared, so it is said to be that the left hand is rising and the right hand is rising as well. Now let's have number 2. If we have a negative leading coefficient, for example, we have f of x equals to negative x squared, wherein we have a leading coefficient that is a negative 1. Therefore, it's a negative leading coefficient. And then we have 2 as a degree, and that's an even degree. So we can say that the left hand is falling and the right hand is falling as well. So that's the behavior of our graph. And then on the third one, if we have f of x equals to x cubed, wherein we have a positive leading coefficient and we have an odd degree wherein we have 3. So the behavior or the end behavior of the graph, now on the left hand we have falling and then the right hand we have rising. And then the fourth one, if we have a negative leading coefficient and then we have an odd degree, so the end behavior for the left hand is rising and then the end behavior for the right hand is falling. So this will be the basis of on how are we going to graph the polynomial. So you're about to have the learning test too. In your answer sheet, you just need to copy and answer the following. So you need to describe the properties of the graph, the given polynomial functions in terms of the standard form, leading term, x-intercepts, and its multiplicities. And then we have the y-intercepts, the number of turning points, possible graph with end behavior. And here you are about to end the sketch the graph, no, for the functions given in part A. And then find the two numbers whose difference is 16 and product of. And then you need to continue answering numbers 3, 4, 5, and 6. So you just need to look for the correct answer in here. The last one, you just need to identify the value of the leading coefficient and the degree of the polynomial functions. So just need to answer number 7 to 16.